Hi, today we're going to look at chemical periodicity, and we are going to use our knowledge of atomic structure to try and explain some of these patterns. So first of all, the properties of the elements and the patterns that we're going to look at today, these patterns come from the periodic table. We're going to look at the atomic radii, ionization energy, and electronegativity. We'll also define all of these properties and look at the periodicity patterns on the periodic table. And we're going to explain these periodic properties using Coulomb's law, the shell model of the atom, shielding, and effective nuclear charge. Again, we will define each of these and then try to use them as explanations for periodic properties. So first of all, in atomic structure, the big picture is that we have these negatively charged electrons that are in a cloud surrounding the positively charged nucleus that is made of protons and neutrons. These attractions of opposite charges of those electrons to the nucleus is the basis of atomic structure. And so Coulomb's law is important to understanding atomic structure. And here is Coulomb's law. The force that, if we are talking about opposite charges, that would be a force of attraction. If we were talking about like charges, this would work for the repulsion force, but in our case of the atom, we're looking at attractive forces between the positive nucleus and the negative electrons, and that force of attraction is equal, it is proportional to, so there's our proportionality K, Q1 times Q2, and that is the magnitude of the two charges, so Q1 and Q2 are the magnitude of the charges, divided by R squared, and that is the square of the distance between those charged particles. So we can see that if we have a more highly charged, something say that's +2 or so, if it's more highly charged, the force of attraction would be greater, and the farther the charges are from one another, then the smaller the force would be. So it's always good to use Coulomb's law when you're thinking about explaining something about charges attracting or the magnitude of the charges that are repelling one another. And so this is good to keep in the back of your mind. Also, we have this shell model of the atom, and it's not currently accepted as the best atomic model, but it is a useful model, and it can help us qualitatively explain some of these atomic properties in our periodic trends. The shell model does reflect the quantum mechanical model of the atom in ways like when we're labeling our orbitals, like as 1s and 2s, these are just examples of the quantum numbers. So if the shell model is not the best model, what is? So for your scientific literacy knowledge, I want to make sure that you know that the quantum mechanical model is currently the best accepted model of the atom. But it's very complicated, and so to use, but it is the best accepted model of the atom. All right, let's talk about shielding. We don't really talk a lot about core electrons like we talk about the valence electrons, but the core electrons do play a role in some of these trends, and these core electrons are the ones that are not the valence electrons, they're the ones that are closest to the nucleus, and they act as a shield for these valence electrons so that these valence electrons don't feel that full attraction of the nucleus. So if we look here at this little diagram, we've got the nucleus in the center, we've got that those protons and neutrons, and then the green little cloud around that nucleus, those would be the core electrons, and they are going to shield that blue cloud on the very outside where those electrons are. Those green electrons, those core electrons, are going to shield our valence electrons, or electrons that we're most interested in here, from that positively charged nucleus. So that's called shielding, and I've seen some books call it screening. So if we look here at the electron configurations of lithium, 1s2, 2s1, that valence electron 2s1 is shielded from the nucleus by the electrons in the 1s orbital. But if we go down to sodium, and the electron configuration is 1s2, 2s2, 2p6, 3s1, that 3s1 valence electron is better shielded from the nucleus. It has that whole, those core electrons, there are 10 of them that are shielding that valence electron from the nucleus, whereas in lithium there are only 2 core electrons shielding the nucleus from the valence electron from the nucleus. Okay, so let's talk about the effective nuclear charge, and its abbreviation is Z effective, and it is defined as the positive charge felt by an electron in the outer shell. It's not the full positive charge of the nucleus, Z, and that is because that positive charge is shielded, like we just talked about, by the inner core electrons. Okay, so now with all of these different explanations, we're going to talk about the periodic properties, and the first one we're going to talk about is atomic radius, and that's basically the size of the atom. And it's the radius of an atom is taken as half of the distance between nuclei. And so here it is in a picture. If we see the chlorine molecule here, we've got the Cl2 molecule, we've got the nuclei is in red there, and the distance between those 2 nuclei is 198 picometers. We divide that in half to get the radius, and we have 99 picometers as our radius for chlorine, and so forth. So the unit is usually angstroms, which is 1 × 10 to the negative 10th meters, and so the atomic radius of lithium is 1.52 angstroms. You can also use the units of picometers or nanometers. Now, what affects how big an atom really is? Well, remember that opposite charges attract, and the nucleus is positive, the electrons are negative, and that electron is going to make up the majority of the volume of the atom, and it's the positive nucleus that's going to be pulling on those negative electrons. So, the atomic radii trend, it depends on how far the electrons are located from the nucleus, and it depends on the positive charge in the nucleus. So let's have a look. This is just a little picture. We've got our transition metals aren't included here because the atomic size doesn't change much with those. But as we go down a group or a family, what's happening is we're adding a shell if we look at the shell model. And as we add a shell, our radius becomes much greater. Also, our valence electrons are more shielded from that nucleus. But as we go across a period, so as we go left to right, we see that the atomic radius decreases. And this is because there's no more shielding. They're all shielded by the same number of core electrons, but what is changing is the number of protons in that nucleus. And so the effective nuclear charge is going up, and it's pulling in those electrons more tightly, thus decreasing the radius. Now, what about ions? Well, cations are always smaller than their parent atom. So like the sodium +1 ion, if we looked at its electron configuration, we will have the sodium ion will have lost its 3s1 valence electron, so it's lost an entire valence shell, where the sodium atom, the Na+, has that 3s1 electron there, and it's added an entire shell. Anions are always larger than their parent atom, and the reason is because you're adding an electron, you're increasing electron-electron repulsion, and remember that like charges repel one another, and thus we are creating a larger electron cloud there. We haven't changed the nuclei of either one of these, the number of protons in the sodium nucleus and the chlorine nucleus, and the chloride nucleus remains the same. It's just what we've done to the electron cloud. All right, let's talk about ionization energy. So knowing this definition is important. It's the energy required to turn an atom into a cation. So in other words, it's the amount of energy required to remove the outermost electron. So let's look at calcium. Its first ionization energy is 599 kilojoules. But then to take away the second electron in calcium, and that's called the second ionization energy, you can see it's a lot greater. Second ionization energies are always greater than the first. But let's think about this trend on the periodic table. The magnitude of the ionization energy is estimated by, well, let's think about Coulomb's law. The farther an electron is from the nucleus, so that would be the R, or the R squared in Coulomb's law. So the bigger that R is, the farther an electron is from the nucleus, it's going to make the force of attraction lower, and so it's going to lower the ionization energy. So electrons that are farther from the nucleus have a lower ionization energy. When we compare electrons that have the same number of electron shells, if you have a higher nuclear charge, so the Q1 or the Q2 is larger, then the ionization energy of an electron would go up. And so the general trend for ionization energy is as you go down a group or a family, the ionization energy goes down. And that's because the electrons are farther from the nucleus. As you go left to right, the nuclear charge is going up, the ionization energy also goes up. All right, and finally, we're going to look at electronegativity, and its definition is also important. And we talked about this a lot when we were in our bonding unit. It's a measure of an ability to attract electrons to itself when it is chemically combined with another atom. So things that like to gain electrons have high electronegativities. So these are things that can attract electrons to itself when they're combined with another atom. And things that have low electronegativities are ones that tend to let go of their electrons a little more easily. And so our electronegativity trend is fluorine is our most electronegative element, and as we go from left to right across the periodic table, the electronegativity increases, and as we go from bottom to top, it also increases. So in general, metals don't really want their electrons, so they have low electronegativity. This is their valence electrons. Nonmetals would like to gain electrons to get the stable electron configuration of an octet, so they tend to have a high electronegativity. All right, so if you would like to look at trends, this is a really cool website that you can go to, and it will give you values of electronegativity, ionization energy, and atomic radius. You can give yourself a quiz, like you can say, hey, who has a greater electronegativity, calcium or magnesium? Make your prediction, and then you can look and see if your answer is correct. All right, so I hope that you now understand these periodic trends, and I hope that you can explain the periodic trends of atomic radius, ionization energy, and electronegativity using either Coulomb's law or combinations of any of these. Coulomb's law, the shell model of the atom, talking about shielding or effective nuclear charge. All right, have a good day.